Welcome to Earth with Nature, a space where we pause to ponder the vast mysteries of our universe with a gentle curiosity. I'm so glad you've joined me today as we embark on a slow, thoughtful journey through the cosmic unknown. Let's dive right into the heart of our exploration. The idea that Earth might be just one of countless worlds in the grand tapestry of the cosmos. What if our planet, with all its beauty and fragility, is not a singular miracle but part of a sprawling gallery of possibilities? Together, we'll wander through the realms of astronomy, exoplanet discoveries, and planetary science, asking questions that stretch our understanding of habitability and life itself. This isn't about quick answers. It's about savoring the wonder of cosmic wonder and letting the questions linger. So, settle in, let your mind roam, and let's uncover the layers of this profound idea, piece by piece, as we marvel at the universe's endless secrets. First, let's ground ourselves in the familiar, our own Earth, a pale blue dot suspended in the vastness of space. Picture it. A world of shimmering oceans, sprawling forests, and towering mountains, all cradled by an atmosphere that shields us from the harshness of the void. Earth exists in what scientists call the habitable zone of our Sun, a narrow band where temperatures allow liquid water to flow, a key ingredient for life as we know it. But what if this perfect balance isn't unique? Astronomy teaches us that our Sun is just one of billions of stars in the Milky Way. And thanks to technology like the Kepler Space Telescope, we've discovered over 5,000 exoplanets, worlds orbiting distant stars. Some of these, like Kepler 452b, dubbed Earth's cousin, sit in their own habitable zones, with sizes and orbits eerily similar to ours. Imagine a planet where alien seas might glisten under a different sun, or where strange forms of life could breathe an atmosphere we can only dream of. Yet, despite these discoveries, no exoplanet matches Earth's exact recipe for life. Our protective magnetic field, the stabilizing influence of our moon, or the delicate balance of gases like oxygen and nitrogen. This raises a profound question. Is Earth a rare gem in the cosmic expanse, or are we just one of many waiting to be found? Consider the exoplanet mysteries. Why do so many worlds we've observed seem too hot, too cold, or too gaseous to support life? Could there be hidden Earth-like planets beyond our current reach, veiled by the limits of our instruments? As we ponder this, let's also marvel at the tech driving these discoveries. Spectroscopy, for instance, lets us analyze the light from distant stars to detect the chemical fingerprints of exoplanet atmospheres, methane, water vapor, or even signs of potential biosignatures. It's like reading a cosmic diary, each line hinting at stories of worlds we may never touch. This blend of science and imagination fuels our emotional connection to the universe, reminding us how fragile and precious our own world is. What do you think? Could there be another Earth out there waiting for us to notice it? As we hold this thought, let's transition to a broader canvas. The sheer scale of the galaxy and what it means for the possibility of life beyond our solar system. Now, let's zoom out to the breathtaking vastness of the Milky Way, a spiral galaxy spanning 100,000 light-years, home to an estimated 100 to 400 billion stars. Each star could host its own planetary system, potentially harboring worlds with conditions ripe for life. This immense scale, illuminated by planetary science facts, suggests that if even a tiny fraction of these stars have habitable planets, the number of possible Earths could be staggering. Think of it as a cosmic lottery, each star a ticket, each planet a chance for life to bloom. Yet habitability is a delicate dance. Take Proxima Centauri b, orbiting the closest star to our Sun, just 4.2 light-years away. It lies in the habitable zone, but its star bombards it with intense radiation, likely stripping away any chance of a stable atmosphere. Contrast this with TRAPPIST-1, a system of 7 rocky planets, 3 of which sit in the habitable zone. Scientists, using the James Webb Space Telescope, are now peering into their atmospheres, searching for traces of water or organic compounds. But even here, challenges abound. Tidal locking might mean one side of these planets is scorched while the other freezes. These findings stir a deep sense of awe and humility. Earth's habitability seems almost orchestrated. Our 24-hour rotation, our 23.5-degree axial tilt creating seasons, and our distance from the Sun ensuring neither ice nor inferno. Reflect on this. Why does Earth seem so perfectly tuned when so many other worlds fall short? Could it be sheer luck, or does the universe favor life in ways we don't yet grasp? The fragility of life's conditions hits close to home when we realize how easily Earth could have been different. A closer orbit, a weaker magnetic field, or no moon to stabilize our climate, and we might not be here to ask these questions. This emotional weight ties us to the search for other worlds. Each discovery feels like a mirror, reflecting our own planet's uniqueness. Let's carry this sense of wonder forward as we explore not just the science, but the philosophical undercurrents of what it means to seek other Earths. How does knowing we might not be alone shift your perspective on our place in the cosmos? As we linger on this, let's pivot to the deeper implications of habitability and the human drive to find, or even create, new homes among the stars. As we linger on the profound implications of Earth's place among countless potential worlds, let's delve deeper into the intricate science of habitability, peeling back the layers of what makes a planet a cradle for life. The concept of the habitable zone, often called the Goldilocks zone, is not just a matter of distance from a star, though that's crucial. It's a symphony of factors. A planet must receive just enough stellar energy to maintain liquid water, neither boiling away nor freezing solid. For Earth, this sweet spot is about 150 million kilometers from the Sun, but it's not a universal constant. A star's brightness and heat output dictate its habitable boundaries. A dimmer red dwarf star, like Proxima Centauri, pulls its zone much closer, while a blazing giant star pushes it farther out. Beyond this, a planet needs a robust atmosphere to trap heat via the greenhouse effect. Too little, and it's a frozen wasteland like Mars. Too much, and it's a hellish pressure cooker like Venus, with surface temperatures hot enough to melt lead at 462 degrees Celsius. Earth's atmosphere, a delicate mix of 78% nitrogen, 21% oxygen, and trace gases like carbon dioxide, strikes a rare balance, maintaining an average surface temperature of 15 degrees Celsius. But habitability isn't just chemistry, it's geology. Plate tectonics, unique to Earth among known planets, recycles carbon through volcanic outgassing and weathering, stabilizing climate over millions of years. Without this, Earth might have succumbed to runaway heating or cooling, as Venus and Mars did. Consider also the role of water itself, a molecule with extraordinary properties. Its high heat capacity moderates temperature swings, and its ability to dissolve a vast array of substances makes it a perfect medium for biochemical reactions. Yet, water's abundance on Earth, covering 71% of the surface, is a cosmic anomaly. Most exoplanets we've studied, like the gas giants of Kepler-11, lack accessible liquid water. Ponder the precision required for all these elements to align. Scientists estimate that only about 1 in 100,000 stars might host a planet with Earth-like conditions, based on current exoplanet surveys. This rarity fuels the rare Earth hypothesis, suggesting that while microbial life might be common, complex ecosystems and intelligent beings require an almost impossible convergence of factors. Reflect on the data from the Kepler mission, which found that only 0.1% of surveyed stars have planets in the habitable zone with Earth-like sizes. What does this scarcity suggest about life's prevalence? Could Earth be a statistical outlier? Or are we underestimating the adaptability of life in forms we can't yet imagine? Perhaps silicon-based organisms on scorching worlds or methane-breathing life in frigid Titan-like environments. The search continues with missions like the European Space Agency's Ariel, set to launch in 2029, which will analyze the atmospheres of 1,000 exoplanets for signs of water vapor, methane, and other life-friendly molecules. This technological frontier, blending spectroscopy with machine learning to sift through vast datasets, offers a glimpse into alien chemistries. Yet, it also deepens the mystery. If Earth's recipe is so specific, how did it come to be? Was it blind chance over billions of years? Or does the universe possess an unseen bias toward life-friendly outcomes? These questions tie us emotionally to our planet, urging us to cherish its oceans, forests, and air, while pushing us to refine tools like the upcoming Large UV/Optical/IR Surveyor, LUVOIR, telescope, which could directly image Earth-like exoplanets by the 2030s. Each discovery is a step toward understanding whether life is a cosmic accident or a recurring theme, and it invites us to marvel at the fragility of the only home we've ever known. Shifting our gaze from the mechanics of habitability to the dynamic role of planetary protectors, let's explore how Earth's cosmic neighborhood contributes to its life-sustaining stability. One of the unsung heroes in Earth's story is Jupiter, the solar system's giant shield. With a mass 318 times that of Earth, Jupiter's gravitational pull acts as a cosmic vacuum cleaner, intercepting many comets and asteroids that could otherwise collide with us. The 1994 impact of comet Shoemaker-Levy 9 into Jupiter, with explosions equivalent to millions of nuclear bombs, demonstrated this protective role. Had such a comet struck Earth, it could have triggered a mass extinction. Scientists estimate that without Jupiter, Earth might face catastrophic impacts 10 times more frequently, disrupting the long-term stability needed for complex life to evolve. This protective dynamic isn't guaranteed. Many exoplanetary systems lack such massive guardians, leaving smaller rocky planets vulnerable to bombardment, as seen in simulations of systems like HD 69830, where debris disks suggest frequent collisions. Equally critical is Earth's moon, a stabilizing anchor. Unlike most planetary moons, which are tiny relative to their hosts, our moon is unusually large, about 27% of Earth's diameter, formed from a cataclysmic collision 4.5 billion years ago. Its gravitational influence slows Earth's rotation, preventing wild temperature swings, and stabilizes our axial tilt at 23.5 degrees, ensuring consistent seasons vital for agriculture and ecosystems. Without this, Earth's tilt could wobble chaotically between 0 and 85 degrees over millennia, as seen in models of moonless planets, leading to climatic extremes incompatible with life. Compare this to Mars, whose small moons, Phobos and Deimos, offer negligible stabilization. Mars' axial tilt varies dramatically, contributing to its frozen, barren state. In exoplanet studies, using data from the Transiting Exoplanet Survey satellite, TESS, astronomers seek systems with large moons or gas giants to gauge their protective potential, though detecting exomoons remains elusive. Only Kepler 1625 b, a candidate 8,000 light-years away, hints at such a feature. This underscores Earth's fortunate setup, but it also prompts curiosity. How many worlds lack these guardians, and does that doom their chances for life? Or could alternative mechanisms, like dense asteroid belts or unique orbital resonances, offer protection we haven't yet modeled? The emotional resonance of this lies in recognizing Earth's vulnerability without these silent sentinels. A single unblocked impact, like the one that ended the dinosaurs 66 million years ago with a 10-kilometer asteroid, reminds us of life's precariousness. Technology amplifies this awareness. Projects like NASA's DART mission, which in 2022 successfully altered the orbit of asteroid Dimorphos, show we can defend ourselves, but only if we act as stewards of our cosmic luck. Consider the galactic habitable zone, a region in the Milky Way neither too close to the radiation-heavy galactic center nor too far in the metal-poor outskirts. Earth sits perfectly within it, avoiding supernovae and gamma-ray bursts that could sterilize life. How many exoplanets, even in habitable zones around their stars, lie in deadly galactic neighborhoods? This intricate web of protection, planetary, systemic, and galactic, paints Earth as a sheltered oasis, deepening our appreciation for its endurance over 4.5 billion years. It challenges us to ask, are such safeguards common enough to expect life elsewhere, or is Earth a uniquely sheltered haven in a hostile universe? Now let's turn to the temporal dimension of habitability, examining how time itself shapes the possibility of life on Earth and beyond. Life didn't emerge overnight. It required billions of years of relatively calm cosmic conditions, a luxury not guaranteed in the violent early universe or in unstable star systems. Earth's history began 4.54 billion years ago, with life appearing perhaps as early as 3.8 billion years ago in the form of simple microbes, as suggested by fossilized structures in Greenland's Isua greenstone belt. This long gestation needed stability. Minimal asteroid bombardments after the late heavy bombardment period around 3.9 billion years ago, a sun that didn't flare too violently, and a planet that avoided catastrophic climate shifts. Contrast this with exoplanets around red dwarfs, which make up 70% of stars in the Milky Way. These stars often unleash intense flares of X-rays and ultraviolet radiation, especially in their youth, potentially stripping atmospheres from planets in their tight habitable zones. Studies of TRAPPIST-1, a red dwarf with 7 rocky planets, show that its early flaring phase might have eroded any initial water or air, leaving desiccated worlds despite their promising orbits. Earth's Sun, a G-type main sequence star, offered a gentler evolution, increasing its brightness by only 30% over 4.5 billion years, allowing life to adapt gradually. Timing also matters in planetary processes. Earth's magnetic field, generated by a molten iron core, has shielded us from solar wind for eons, preserving our atmosphere, while Mars lost its dynamo early, its atmosphere thinning to 1% of Earth's pressure. This protection isn't eternal. Earth's core will cool in billions of years, weakening the field, but for now, it's a vital shield. Reflect on exoplanet data. The James Webb Space Telescope's 2023 observations of K2-18b, a sub-Neptune 120 light-years away, hint at water vapor and methane, but its star's activity might preclude long-term habitability. How critical is this cosmic patience for life to take root and evolve complexity? Could life adapt faster under harsher conditions, or does it universally need Earth's billions of quiet years? The emotional weight of time strikes when we realize life's journey, from single cells to sentient beings, hinges on epochs of stability we often take for granted. Technology extends our view of time. Isotopic dating of meteorites and lunar rocks maps our solar system's timeline, while astrobiology models predict habitability windows for exoplanets based on stellar lifespans. Red dwarfs last trillions of years, offering vast time for life if radiation doesn't kill it first. This temporal fragility mirrors Earth's future. In 1 billion years, the sun's increasing heat may evaporate our oceans, ending habitability unless humanity intervenes with geoengineering or migration. Such forecasts, grounded in simulations from the Potsdam Institute for Climate Impact Research, evoke a poignant sense of urgency to protect our window of opportunity. Consider the anthropic principle. We observe a universe suited to life because we exist to see it. But does this explain time's alignment, or merely restate the mystery? How many worlds had the right conditions but lacked the eons to nurture life? This long arc of time, from Earth's primordial soup to today's biodiversity, underscores life's persistence, yet also its dependence on a clock that could have run out at any moment, urging us to value every second we have to explore and understand. Finally, let's weave together the threads of habitability, protection, and time to ponder the broader implications for life's cosmic distribution and humanity's role in it. The search for other Earths is not merely academic. It's a mirror to our own existence, reflecting both our uniqueness and our shared potential with the universe. Astrobiology, bolstered by missions like NASA's Perseverance rover seeking ancient microbial traces on Mars, suggests life might arise wherever conditions allow, perhaps in Europa's subsurface ocean or Enceladus geysers, both harboring water and energy sources. Yet, Earth stands apart with its staggering biodiversity, from deep-sea vents to rainforest canopies, a complexity unseen elsewhere. Exoplanet surveys, with over 5,500 confirmed worlds as of 2023 per the NASA Exoplanet Archive, reveal a spectrum of possibilities. Super-Earths like LHS 1140b, with potential oceans, to mini-Neptunes with thick hydrogen envelopes hostile to life as we know it. Statistically, the Drake equation estimates the number of communicative civilizations in our galaxy, factoring in star formation rates, about 1.5 new stars per year in the Milky Way, planetary prevalence, roughly 0.1 habitable planets per star, and life's likelihood. Yet even optimistic inputs suggest we might be alone or one of few within reach. This solitude or rarity carries emotional heft. It positions Earth as a precious outlier, a garden in a desert of stone and gas. Technology, from SETI's radio scans to the upcoming Vera C. Rubin Observatory's survey of transient cosmic events, seeks neighbors, but silence persists. What if life is common but fleeting, snuffed out by stellar tantrums or self-destruction before it can signal? Or what if intelligence itself is the bottleneck? As evolutionary biology suggests, consciousness might be a fluke even on life-rich worlds. Ponder the Fermi paradox. If life abounds, where is everyone? This silence fuels both hope and dread. Hope for discovery, dread of isolation, or of finding ruins of fallen civilizations. Humanity's role emerges here, with projects like SpaceX's Starship aiming for Mars colonization by the 2030s, or concepts of interstellar arcs. We might seed life elsewhere, becoming creators of new Earths. But this ambition demands ethics. Should we alter worlds, risking native ecosystems we can't yet detect, as debated in astrobiology ethics forums? Earth's own fragility, with climate models predicting a 2°C rise by 2100 potentially disrupting habitability per IPCC reports, mirrors the stakes. Each exoplanet studied, like the temperate TOI 700d 101 light-years away, is a reminder of what we could lose or gain. Emotionally, this ties us to a dual mission: preserve our blue marble while extending life's reach, a legacy of curiosity and care. How do we balance exploration with stewardship, ensuring we don't repeat Earth's scars on alien soils? This cosmic perspective reshapes identity. We're not just inhabitants but potential guardians of life's flame, tasked with understanding habitability's rules. Atmospheric balance, gravitational shields, temporal windows, to apply them wisely. As we gaze at the night sky, each star a question mark, let's commit to unraveling life's cosmic story, knowing Earth might be one of many, or one of none, but always the heart of our quest. Diving deeper into the cosmic narrative, let's explore the intriguing concept of life's adaptability and how it might challenge our Earth-centric view of habitability. We often frame life through the lens of carbon-based biology, reliant on liquid water and a narrow range of temperatures, because that's what thrives here. But what if life, in its boundless creativity, defies these constraints on other worlds? Astrobiologists speculate about alternative biochemistries, silicon-based life, for instance, which could theoretically function in high-temperature environments where carbon bonds would break down. Silicon, like carbon, can form complex molecules, though its chemistry is less versatile and stable. Imagine a planet near a hot star, with surface temperatures exceeding 500 degrees Celsius, where molten silicon rivers nurture strange, crystalline organisms. Such ideas stretch our imagination, but they're grounded in chemical possibility, even if no direct evidence exists yet. Closer to home, consider Titan, Saturn's largest moon, with its lakes of liquid methane and ethane at a frigid -179 degrees Celsius. Could life there use hydrocarbons as solvents instead of water, metabolizing in ways alien to us? NASA's Dragonfly mission, set to launch in 2028, will explore Titan's surface for prebiotic chemistry, seeking clues to such exotic life forms. This pushes us to rethink habitability, not as a fixed recipe, but as a spectrum of possibilities shaped by a planet's unique conditions. Reflect on Earth's own extremophiles, organisms thriving in environments we once thought impossible. Thermophiles in Yellowstone's boiling hot springs at 80 degrees Celsius, or tardigrades surviving the vacuum of space. If life here adapts to such extremes, couldn't it elsewhere, under radically different rules? The emotional pull of this idea is profound. It suggests life might be far more tenacious and widespread than we dare hope, hiding in cosmic corners we've dismissed as barren. Yet, it also humbles us. Our search tools, like spectroscopy, are tuned to detect Earth-like biosignatures, oxygen, methane, water vapor, potentially blinding us to alien life forms that leave no familiar trace. What if we've already observed a living world but missed its signals? This uncertainty fuels missions like the European Space Agency's JUICE, launching in 2023 to study Jupiter's icy moons, probing for subsurface oceans where life might lurk in forms we can't predict. It invites us to broaden our cosmic empathy, to see every planet, even those deemed uninhabitable, as a potential canvas for life's art. How does this shift your view of what a home in the universe could be? Let's carry this expansive mindset as we pivot to the role of stellar environments in shaping these diverse possibilities for life. Zooming out to the stellar stage, let's consider how the type and behavior of a star dictate the habitability prospects of its planetary companions, often in ways more complex than just the habitable zone's boundaries. Our Sun, a stable G-type star, has provided a consistent energy output for billions of years, but not all stars are so accommodating. Red dwarfs, the most common stars in the Milky Way, comprising about 70% of the galactic stellar population, burn cool and slow, with lifespans stretching into trillions of years. This longevity seems ideal for life to develop over vast timescales, yet their temperament poses challenges. These stars frequently emit powerful flares of X-rays and ultraviolet radiation, especially in their early active phases, which can strip atmospheres from closely orbiting planets in their tight habitable zones. Take the case of Proxima Centauri, our nearest stellar neighbor at 4.2 light-years away. Its planet, Proxima b, sits in the habitable zone, but studies using data from the Chandra X-ray Observatory suggest it endures radiation levels 100 times higher than Earth, likely eroding any protective atmosphere long ago. Conversely, larger, hotter stars like F-type or A-type burn brighter and die faster, often within a few billion years, potentially cutting short the evolutionary timeline needed for complex life. Planets around such stars, even if initially habitable, might face a cosmic deadline as their star swells into a red giant, engulfing inner orbits. Earth's Sun will meet this fate in about 5 billion years, expanding to swallow Mercury and Venus, and possibly scorching Earth. This stellar diversity, revealed through surveys like Gaia's mapping of over 1 billion stars, shows that habitability is a moving target, tied to a star's life cycle. Emotionally, this underscores the fragility of life's window. Even Earth, so perfectly placed now, is on borrowed time. It also sparks curiosity. Could life migrate between systems as stars die, carried by comets or intentional probes, a concept known as panspermia? Technology lets us probe these stellar influences. The Transiting Exoplanet Survey Satellite, TESS, targets bright, nearby stars of various types, cataloging over 6,000 candidate exoplanets by 2023, helping us correlate stellar properties with planetary conditions. Consider TRAPPIST-1 again, a red dwarf with 7 rocky planets. Despite flare risks, its dim light means planets must huddle close, increasing chances of tidal locking, where one side perpetually faces the star, creating extreme temperature contrasts. Could life adapt to such a split world, thriving in a twilight zone between day and night? This interplay of star and planet deepens our awe at Earth's cosmic luck, orbiting a star neither too volatile nor too short-lived. How might life differ under a red dwarf's eternal dusk versus a bright, fleeting giant's glare? Let's hold this stellar perspective as we shift to the galactic context, exploring how a planet's position in the broader Milky Way influences its chances for life. Stepping further out, let's examine the Galactic Habitable Zone, GHZ, a concept that extends the idea of habitability beyond individual stars to the structure of the Milky Way itself, revealing yet another layer of cosmic privilege for Earth. The GHZ is a ring-shaped region, roughly 25,000 to 30,000 light-years from the galactic center, where conditions are thought to favor life. Too close to the center, and a planet faces intense radiation from densely packed stars, frequent supernovae, and gravitational disruptions from the supermassive black hole at the Milky Way's core, Sagittarius A star. Such events could sterilize worlds or destabilize orbits, as modeled in simulations of galactic dynamics. Too far in the outskirts, beyond 40,000 light-years, and stars lack the heavier elements, carbon, oxygen, iron, forged in earlier stellar generations, elements essential for forming rocky planets and life's chemistry. Earth sits comfortably at about 27,000 light-years from the center, in a spiral arm with moderate star density, avoiding both the chaotic core and the sparse rim. Studies, such as those from the University of Washington in 2001, estimate that only 10 to 20% of the Milky Way's stars reside in this GHZ, narrowing the pool of potential life-bearing systems. This galactic placement isn't just about safety, it's about resources. Our position grants access to a mix of old and young stars, providing a steady supply of materials via stellar winds and explosions, enriching the interstellar medium over billions of years. Contrast this with exoplanets detected near the galactic bulge, like those in the OGLE surveys, where high stellar traffic increases collision risks and radiation